I'd like to thank organizers for giving me a chance to speak at such a wonderful workshop. In this workshop, what I'm going to talk about is my work with, which is in progress with Shumanshu from TFR and Shubho from IITH. And I expect a paper to be out soon in a week or two. So the title of my talk is The Holographic Complexity of a Little String Theory. And the plan of the talk, first I'll give a general introduction, followed by what is computational complexity and its holographic realization, then followed by a worldsheet sigma model and LST. Then we'll see its one realization, which is an example, followed by certain features which it has, and then I'll give the details of the computations for the zero temperature CV and CA, and as well for the finite temperature case. And later I'll conclude my talk. So the general introduction. One of the chief lessons to draw from holography is the bulk geometry is encoded in the boundary state entanglement structure. The first example to see holography at work is brought forth by Maldacena in 2001, is that of the eternal EDS black hole, which is represented in the CFT by maximum.
Hello, is there a question?
Okay, sorry. Okay. So this is a realization of the eternal ADS black hole, which is represented in the CFT by a maximally entangled two CFTs. Then followed by the work of Ryu Takanagi in 2006, in which some boundary state entanglement is written in terms of the maximal surface in the bulk. Later, we see that Brian Schwingel his work on MERA, which is a multi-scale entanglement renormalization in SATS, who gave the discrete realization of the bulk space-time in terms of the boundary state wave functions. Then we see this work by Ramstonk in 2010, who stated that CFT entanglement structure is crucial for having spatial connectivity, and which is also evident in the work of LMPS in 2012, where we see that the lack of entanglement across the horizon is responsible for the lack of smoothness or the existence of the firewalls. And then there is this popular slogan ER is equal to EPR by Maldacena and Susskind, where ERB, which is Einstein-Rosen bridge, in the bulk is stated to be equivalent to some sort of Bell-pair entanglement in the boundary. Computational complexity. Now, this has been very thoroughly reviewed in earlier talks, but for the sake of completeness, I would like to just go over it. So complexity is a term borrowed from the computer science and quantum information theory literature. Basically, it quantifies the difficulty of performing a task. But in order to define it, what we need, the ingredients which go into defining it are the system, the set of states. Then there's a reference state, the target state, and some set of simple, well-defined, simple operations. So complexity of a state A relative to the state O, A is called the target state. The complexity of the target state relative to that of the reference state O is given as is defined as the minimum number of simple operations we need in order to go from O to A. Classically, the picture we have in the mind is of the system of n classical bits, which is like classical spins or coins. The simple operation would be like flipping of the spin or the coin, and there's no distinction between the complexity and the entropy. Both scale equally, like with the degrees of freedom. But in quantum mechanics, however, in the quantum mechanics, due to the superpositions, we now, instead of the k binary digits, now we require 2 raised to power n complex numbers to specify a state. So that's the origin of the drastic difference between the classical entropy, classical complexity and the quantum complexity. The quantum complexity scales as exponential in the degrees of freedom. Now this is let's look at the behavior of evolution of the complexity of the quantum mechanical system. Yeah, so initially we see that the complexity, it exhibits linear growth. Complexity and entropy both increases until entropy hits its maximum at the thermalization point. Yeah, so this is the conjectured linear growth, which we see here. And the entropy, it hits maxima at time thermalization times, which are order of, which are like polynomial in degrees of freedom. Whereas yeah, entropy also hits its maxima here, but whereas we see that the complexity still keeps on increasing, and it still keeps on increasing until it hits the maximum at time t is equal to exponential in the number of degrees of freedom, where its value is also exponential in the number of degrees of freedom. Then it stays there for a very long time as the system evolves, and that is due to because there are a lot of states which are exponentially complex. Then after the Poincare recurrence time, which is double exponential in the degrees of freedom, this system comes back to the initial state. Uh, yeah, so the holographic realization of the boundary complexity in bulk in terms of the ERB is been proposed by Susskind in this work. What is proposed that the complexity is giving us some sort of maximal volume slice in the bulk, and then there are these constants which are there for some dimensional reasons. And yeah, so what we do that we anchor this space like slice at some boundary time t, and we carry out the variational problem in which we vary that, and uh, and the maximum volume slice gives us is conjectured to give us the complexity of the boundary state. Then there's an alternative formulation due to Skyne, where he proposed that the complexity of a boundary state is given by the on-shell bulk action, which also includes these boundary terms, which is evaluated over the Wheeler-DeWitt patch. Wheeler-DeWitt patch, which is anchored at the boundary times. Now we see that this Wheeler-DeWitt patch is a union of all the space-like slices which join TL and TR. And yeah, so first term here we see this is the regular Einstein-Hilbert action. Then there is the Gibbon-Hawkins York boundary term, and then followed by some counter terms which correspond to these joints where two boundaries meet. And these counter terms are required for in order to make this action principle well defined. Now, we compare and contrast their utilities. So complexity encodes like I said, the ERB volume, which we see in this figure is the region behind the horizons. And sorry, yeah. So as time evolves, we expect our ERB volume to evolve, and this feature is clearly visible in the CV formulation of the complexity. But then there is, we see also, yeah, sorry. But there is this appearance of some ambiguous characteristic length scale, which is a little undesirable feature of CV. And also the CV prescription is a variational problem. It's a little difficult to solve operationally. And here is where this complexity action proposal that comes in handy, because we just have to evaluate the integrals and we don't have to deal with this variational problem. And it's also free of the arbitrary length scales, and CA, unlike CV, has a universal appeal, because you see these are just the universal constants sitting in the definition of the action complexity. Yeah, so I would also like to state that in our calculations, where two null boundaries meet, we deform those null boundaries to a single time-like slice by introducing this regulating surface by putting in a regulator. The utility of doing this is that we can carry out the regular GHY integrals without worrying about the counter terms. And this GHY is already a diffeomorphism invariant, reparametrization invariant. And that's why we, in this way of approaching, of dealing with this problem, it removes the need to evaluate the full null that null joint terms here, because these are two null boundaries. Okay, so next is let's come to the main part of the talk, which is the exploration, which is mainly this LST M3 correspondence. So explorations in holography so far has largely restricted to the ADS backgrounds, and perhaps it will be nice if it can be extended to other backgrounds like flat or de Sitter. My talk will focus on perhaps lesser known variant of this holographic duality, which is LST M3 duality, little string theory and M3 duality, and is still being worked out by people like Katoch, Sumanshu, Givion, and I'll show you some results of complexity of LST M3 using this Suskind's holographic proposal, which will also reveal some exotic features which are not encountered in the local field theories. So what we have in the bulk is the type 2 superstrings on ADS 3 cross S, 3 cross T4 with the NS sector turned on and RR fluxes switched off. Now, this is a worldsheet theory in which is given by the West-Zumino-Witten sigma model on SL2R gauge group. It's a holographic string theory where the boundary dual is an irrelevant single trace deformation of the boundary theory, and this corresponds in the bulk theory to a marginal deformation, which is solvable. So the resulting string theory background thus obtained is called M3, and here is the metric. Here is the dilaton and the NS3 form field. Yes, and one example, one realization of this is NS5 plus N plus F1 system. So this example, we have a stack of N coincident NS5 branes wrapping around a 4-dimensional compact manifold, which is T4. And along with that, we have P F1 fundamental strings, which are wrapped around S1. The near horizon geometry of this NS5 plus F1 is ADS3. And near horizon geometry of NS5 branes is that of a flat spacetime with a linear dilaton. This M3 background, this interpolates between the linear dilaton spacetime in the UV to the ADS3 spacetime in the IR. Next, this boundary theory, the dual boundary theory, it interpolates between the CFT2 in the IR to the 2-dimensional little string theory in the UV. So this LST has a few nice features. The nice thing is that it's intermediate between the local quantum field theory and the critical string theory in the following way. First of all, it's a non-local field theory. That is, at local distances, it's not governed by a fixed point. And at high energies, the Hagedorn density of states, it has the Hagedorn density of states. Its entropy goes proportional to the energy. Thirdly, it does not have gravity, and that is, it does not have any massless spin 2 excitations, and but it also has well-defined off-shell green functions like in the quantum field theory. So these first two features, which are common with critical field theory, and last two with the quantum field theory, in this way, this LST is the kind of hybrid between the this critical string theory and the quantum field theory. It's a non-local field theory. So so next over to the computation of zero temperature, complexity of zero temperature M3. This is the gravitational action. Here is the, so this is the Einstein-Hilbert action term. Then we have a dilaton. Then we have a 3-form gauge field, and this is the cosmological constant. The metric is for a zero temperature case is given by this, where R5 is related to the ADS radius. This lambda is a parameter which tunes tunes you between the ADS and the M3. It's a kind of the tuning parameter. Then the dilaton is given by this equation. And so we compute the CV for the zero temperature.
Gaurav, can I ask a question?
Yes.
Can you go back to your previous slide? So you mentioned that the NS5 geometry is governed by K branes, and there is string coupling and string length. Those parameters are not visible here. Can you tell us what these parameters lambda, R1, and R5 are in terms of those?
Yeah, I have included it in the slide, but it is given in the paper by Sumangshu, and the dictionary can be worked out of work using that reference.
But what is this lambda parameter? Is it related to the number of branes?
Yeah, lambda is equal to the number of branes divided by the radius of the cylinder, which is on which your CFT lives.
And what is little r1?
Little r1 is related to the string coupling, Newton's constant, and the number of F1 strings which you have in your system.
So if I tune r1 to 0, which parameter am I setting to 0?
You are set. Yeah, you are. You are setting F1 strings to 0 because it's proportional to P. P is the number of F1 strings that we have wrapped around the S1.
And r5 is what, the ADS radius, ADS3 radius?
M5 is the ADS radius, yeah. And the lambda tunes you between this M3 and the ADS3 in the deep bulk.
Okay, go ahead.
Yeah. All right, so the complexity of zero temperature M3, this is the volume generally looks like. We execute that the variational, we apply the variation principle, we solve the
Gaurav, I
Euler-Lagrange
have a
equations
question.
and
Hello, Gaurav, I have one more question.
yes,
Why
yes.
is there e to the minus 2 phi in the volume functional?
Because it's written in terms of the string frame, and this is the conversion factor. You go from the Einstein metric to the string frame metric.
Okay.
Yeah. All right, so you have this volume. This is the general volume, looks like this. And then you set up a variation principle, you solve the Euler-Lagrange equation, and then you arrive at, but here it is very easy to do because the geometry for a zero temperature case, because this geometry had the time reflection symmetry. And this means that you can yeah, you can change your t to minus t in the metric and it does not change anything. So this meant that the spatial slice is just t equal to constant from symmetry reasons. So this is simple to solve. You plug t prime equal to 0 and you solve for complexity. But the novel feature which appears here is that you can see that in the context of the local quantum field theory, we expect complexity to show because since the complexity is an extensive quantity, so it is expected to be a scale up to proportional to the degrees of freedom. So, but here you see that this is a novel feature that complexity is coming to be proportional to the lambda squared. And maybe this is a reflection of the fact that the boundary theory is a non-local little string theory. So this fact is not visible in case of the local quantum field theories where we expect it to be linear proportional to the cutoff. And another thing, you have this log term here. Its coefficient might be some universal, might have some universal appeal. But we also compute the CA to check with those results. So these are the results of the CA for zero temperature case. So bulk action, you have this log square term, which is again novel, and we so far have no intuition from the point of even from the LST point of view or the TT bar point of view. And the comments are welcome at the end of the discussion as what interpretation can be attached to such a term. Then again, here we see that, yeah, so this is the boundary term, boundary action term. This basically, yeah, so these are the boundary GHY terms. And the one feature which is visible in all of them is that there's a lambda squared dependence, just like in the CV case. And maybe it is the reflection of the field theory being a non-local field theory. And next we do the case for the finite temperature M3. Here, this is the horizon, and the volume looks like this. Yeah, we solved it. We try. Yeah, so we plugged it in the Euler-Lagrange equation. We get a highly nonlinear equation, and it is difficult to solve. Maybe it can be solved perturbatively in the power of rho plus square, where rho plus square is the horizon radius square. But we ventured into its evaluation using the CA procedure. And here again, the bulk action you see is this. There is again appearance of the log lambda square term. And but nice thing, there's one thing that it depends upon, there's a dependence upon the time scales. This is the right and left times on the CFT boundary. And then again, there is a lambda square dependence, so it is visible in all of the terms. And the singularity surface contribution gives you this is again TR plus TL, and this comes from the region behind the horizon. So this part where TR plus TL features, so it comes from the evaluation of the CA computation done on the region 2 which is behind the horizon. And the null boundary contribution, is this. So again, you see this feature, lambda square feature, and there is this, this is order of 1 number, which is some function of rho plus squared. So so this is the result. Now I'll conclude my slides. So so what we see is that the complexity reveals some exotic divergences which are not encountered in the local field theories. This is expected since the dual theory is not a local field theory, but it's a little string theory. And the question is, does the coefficients of these log lambda, these log square terms, do they have any special universal significance? Like we recall that the coefficient of log term in the entanglement entropy came out to be proportional to the central charge. Next, this subregion complexity would be interesting. Interesting case as well, as one can expect to see some Hagedorn phase transitions. This is just like perhaps on the same lines as the in the work cited before of Sumangshu, where he has evaluated the entanglement entropy. And another thing which in the future direction, I would like to say that exploring other irrelevant deformations of the CFTs along the line of this deforming the good old CFTs with these irrelevant deformations. Maybe this will give us a new way in which to embark on the journey of exploring the frontier of non-local field theories by deforming by some non-local these deformations. Thank you.
Okay, thank you for the talk, Gaurav. Are there any questions from the audience? Okay, if there are no questions from the audience, then can I ask a question of my own? Gaurav, can you go back to your couple of slides? So I'm just curious, in your expressions for the complexity volume and complexity area. So the complexity area and complexity volume, what you're saying is they're in disagreement because you have a log square term in the area action. Yeah, and instead in volume you don't get this. One more thing, are there finite pieces?
Yeah, there are finite pieces. I have just kept these leading order pieces. There are finite pieces.
Because in yesterday, Pratim's talk, he was mentioning that the finite pieces look very much like those you could get from entanglement entropy. Okay. So perhaps you can compare your results with Shamangshu's entanglement entropy for subregions and check.
The main idea of the talk was just to focus on this feature, which is a novel feature of working with the non-local field theories, this appearance of which is you don't encounter normally in the local field theories, So I kept only these terms, but there are other terms, of course.
Okay, so if there are no more talks, we'll say goodbye to Gaurav. You can unshare your screen.
Thank you. Thank you. Thank you for your time.